So up until this point in the year, we've been talking about derivatives and how those relate to instantaneous rates of change. In last class, we talked about antiderivatives and what those look like. Today, we're going to kind of go in a different direction, and we're going to be talking about how a rate of change can relate to an accumulation of area. So what we're going to do is we're just going to kind of take a basic problem that we would be able to solve even without calculus, and then we're going to be talking about how that relates to an antiderivative type function. So let's say that we're on a road trip and we have our car on cruise control for 4 hours. So that means that we're not changing speed, we're just staying constant speed. And it's telling us that we're traveling at a speed of 60 miles per hour. We want to know how far we've traveled. So even without calculus, we can kind of think about this as, okay, well, distance is rate times time. Our rate is 60 miles per hour and our time is 4 hours. If we multiply those two together, that's going to give us what our total distance would be. So we want to ultimately know how far we've traveled. So we know it should be 60 times 4, which would give us 240 miles. But let's look at this graphically. So here I have speed on my y-axis and I have my time in hours on my x-axis. So I'm just going to make some labels here. And I'm going to count my speed by, let's do tens. So if I have my car on cruise control and I'm not changing speed at any point during this 4 hours, my function is going to be constant. So if I'm traveling at 60 miles per hour, my function is probably going to look something like this. And we said that we are looking for the distance that we've traveled after 4 hours. So if we think about this as an area, we know that we're looking for really multiplying 60 times 4. Well, the number of units on my x-axis is 4. The number of units on my y-axis would be 60. What we're really doing is we're really kind of taking that accumulation of distance as an area under this curve, because we know that the area of a rectangle is just length times width. And in this case, we're multiplying our speed of 60 miles per hour times our time of 4 hours. And we'll notice that our units of hours actually end up canceling out here, and we're just left with 60 miles, which, I'm sorry, not 60, 240. 60 times 4 is 240. So what we can say is the distance, or how far we've traveled, is actually the accumulation of the rate of change. And this is a rate of change graph because we know that we are taking a speed, and that's what we were graphing. So how far you've actually traveled after however many hours or whatever the time period is actually the accumulation of the rate of change. And we can also say that the distance that we've traveled in 4 hours by a car moving at 60 miles per hour corresponds to the area of this rectangle. And if we kind of get a little bit more specific, not only is it the area of the rectangle, it's actually the area that's contained underneath the curve, which is going to be kind of an idea that we're going to work with a lot this unit. So I'm going to kind of make that a little bit more specific, and I'm going to say the area represents how far you have gone over a particular time period. And that's going to be the area that is contained underneath the curve. So let's look a little bit more at that idea of what the area under the curve looks like, because like I said, we're going to be working with that a lot during this unit. And we can say that the region between a function and the x-axis is called the area under the curve. So we kind of use the general term as area under the curve, but we're really talking about the region between the function and the x-axis. And this can look a couple of different ways. So under doesn't actually necessarily mean below. It just means that the area is contained between the x-axis and the function. So for example, here's our function, the first graph, here's our x-axis. The area under the curve is actually legitimately the area that's trapped underneath the curve. But again, it's contained within this x-axis. The second graph is actually below the x-axis. So a lot of people kind of want to say that the area under the curve would be this stuff that's actually underneath it, but it's actually going to be the area that's trapped between the curve and the x-axis. So it's actually going to be the area that is trapped above the curve. And then a function might look like this, where there's some area above and some area below. So sometimes you might have some area that is actually trapped above the curve and below the x-axis, or below the curve and above the x-axis. So in this case, we've got a couple of different regions that are below the x-axis, and one region that's above the x-axis. So when we talk about the area under the curve, again, it doesn't necessarily mean that it's always going to be under the curve. It's going to be that area that's trapped between the x-axis and the function. And we'll look kind of more at an example of what a curve like that would look like in our last example today. Okay, so let's get back to this idea of area under the curve. So the graph below is representing the rate. Again, we need to have a graph of a rate in order to use this idea of accumulation or area under the curve. So the graph below represents the rate at which water is leaking out of a tank. The units are given in the graph. So it looks like our units of time are minutes, and it looks like our units on the y-axis is gallons per minute. We want to know how much water has leaked out of the tank after 9 minutes. So what we're looking for is how much water. So our units, remember that kind of when we multiplied our units in the last one, we were really multiplying our units of the y-axis by our units of the x-axis. So if you were to multiply gallons per minute by minutes, that's going to give us a unit of gallons that should be left after our minutes cancel out. So we're looking for a number of gallons. And in this case, the area under the curve looks a little bit different, because if we look to see, here's our starting time and here's our ending time, we've got a lot of different shapes going on here. And it's up to you really how you want to split them up. Usually I try to kind of look for the largest areas that I can kind of split up into simple shapes. So we're looking for an accumulation of the amount of water that's leaked out. So I'm going to split my shape. I'll kind of use this like big rectangular region first to kind of calculate what this area under the curve would be. So it looks like my base here would be 6, my height would be 2. So it looks like the area under this part of the curve, the rectangular region, would be 12. And then it looks like I've got a semicircle up here on the top. So semicircle, my area would be 1/2 pi times the radius squared. Looks like our radius here would be 2 units. So 1/2 pi times 4. Looks like our area in this region up here, the semicircle, would be 2 pi units. And then it looks like we've got kind of this little triangular region down here. So it looks like my area would be 1/2 the base times height. Base here is 3 units. Height here would be 2 units. So 1/2 times 6 should give me an area of this triangular region of 3 units. So if we're looking for the total amount of water that's leaked out, what we're really just looking to do here is adding all of our areas together. So total amount of water that's leaked out would be 12 plus 2 pi plus 3. So it looks like our total amount of water that's leaking out would be 15 plus 2 pi gallons of water. So here we were looking for the total accumulation from the time that we're starting to the time that we're ending. So it looks like we're just looking for what is that total area under the curve. If I was just looking for the total amount of water that's leaked out of the tank after 6 minutes, well, then I would just be looking for the area that's over here with the rectangle and the semicircle, and I wouldn't want to include on the triangular region. So it really just depends on what your unit of time would be. Okay, so let's look at a distance problem. So we're talking about a particle. So we're going to be kind of talking about those particle problems again in this unit. So a particle starts at x is equal to 0, moves along the x-axis with a velocity. So remember that velocity is a rate of change. Because remember that the velocity is our derivative of our position function. So we are talking about a rate of change curve here again. And this time we're given a formula for the v of t function. So we know that it's moving with a velocity of v of t equal to 3t plus 2 units per second for any t greater than or equal to 0. We want to know how far away from its starting point the particle is at t is equal to 3 seconds. So if I'm looking for how far away it is, I'm looking for what is the total distance it has moved in the 3 seconds. If I'm looking for total distance, again, I'm looking for the accumulation of the area under the curve. So let's take this function and let's graph it. So we know that we've got an y-intercept of 2. We've got a slope of 3. I want to get to at least t is equal to 3, so that gives me my 3 there. And this function would keep on going. If I were to kind of get a bigger coordinate plane or a bigger graph going here, it's not just going to stop. But I am just looking for the accumulation after 3 seconds. So I'm going to kind of cut off my graph here. A little bit off. And I want to know what is this area that's contained underneath this curve and within the x-axis. So here it looks like I've got a couple of different shapes that I can split this up into. Looks like I've kind of got this bottom rectangular area and this top triangular area. So base times height here, bottom length of 3, height of 2. Looks like the area of this rectangular region would be 6 units. And then up here, my triangular piece, 1/2 the base of 3 times the height of 1, 2, 3, 4, 5, 6, 7, 8, 9. If I take 1/2 of 27, that's going to give me 13.5. So the area of this triangular region up here would be 13.5 units. So that's going to tell me that my particle from the time t is equal to 0 to the time t is equal to 3 is going to be moving a total of this area under the curve. So my total distance after 3 seconds is going to be a total of 6 and 13.5. So it looks like my particle would be moving 19.5 units away after 3 seconds. Okay, and we're going to talk more about kind of the particle problems that we talked about back in chapter 2. So this idea of the particle motion, again, is going to keep on coming back. Okay, so we're going to kind of bring some of those ideas back in this next problem as well. So a squirrel starts at building A at time t is equal to 0 and travels along a straight wire connected to building B. Between 0 and 18 seconds, the squirrel's velocity is modeled by this piecewise linear function below. So we got a t is equal to 0, we got a t is equal to 18, and this function is representing its velocity, which again is a rate of change graph that we're looking at. So this is a graph of, if we want to say, v of t. So just a kind of a couple things to keep in mind from what we were talking about with those original particle problems. We want to keep in mind where this graph is relative to the x-axis. So originally when we were talking about the velocity of a particle, we said that when v of t is positive, we know that the particle would be moving in a positive direction. Or in this case, we can kind of generalize and say that that would probably be to the right, that the particle or whatever our object is moving. But if we're talking about the graph of the derivative or the graph of velocity, we know that the graph of v of t is positive when it's above the x-axis. And we can also say the opposite. Well, when v of t is negative, we know two things. We know it's moving in a negative direction, which probably means that we're moving to the left. And we know that the graph of v of t is negative when it's below the x-axis. Okay, so we know a couple things. We know that our graph is above the x-axis up here, and we know our graph is above the x-axis up here, so that must mean that we are moving in a positive direction up above the x-axis. We also know that we have a piece of our graph that is below the x-axis, so we know that our object, or in this case our squirrel, must be moving in a negative direction down here when the graph is below the x-axis. So question A is asking us at what times in this interval, if any, does the squirrel change direction? We want to give a reason of why. Well, think back to the particle problems. We said that the particle changed direction when v of t was equal to 0. So in this case, our squirrel is going to be changing direction when our v of t is equal to 0. So if we look at our graph, well, we know our v of t is positive up here. We know our v of t is negative down here. Well, v of t must be 0 where we're crossing the x-axis. So we're saying that v of t is equal to 0 at t is equal to 9 over here, and v of t is equal to 0 at t is equal to 15. So I'm going to say the squirrel changes direction at t is equal to 9 seconds and t is equal to 15 seconds. And I'm going to say that is because that is where v of t changes signs. Meaning it's either going from a positive velocity to a negative velocity or from a negative velocity to a positive velocity. So again, kind of keep in mind the particle problems. We said that the particle changed direction when the v of t was equal to 0. That's how we got our critical numbers. We would set v of t equal to 0. Same idea here. So then part B is asking us at what time in the interval, or times, I guess, is the squirrel farthest from building A? So if we're looking for how far or when it is the farthest, what we are looking for is what is the maximum distance. So when is it furthest? When does it have the maximum distance away from building A? And then we also want to know how far away from building A is the squirrel at this time. Well, if we're talking about maximum distance over an interval, remember our absolute maxes and our absolute minimums from the last unit, that's going to come into play here. So what we're looking for is we need some critical numbers to test. And if we're given an interval, remember that we always want to include the endpoints of the interval as kind of our starting point and ending point. So we know that we want to include the starting of t is equal to 0. We want to include the ending of t is equal to 18. And then we need to have some values to test in between here. Well, the values that we're going to be testing in between are going to be our critical numbers here. So we're also going to be testing in between the t is equal to 9 seconds and the t is equal to 15 seconds. And what we're looking for is we're looking for the distance that the squirrel has traveled at these particular times. So remember last time we kind of set up a T chart and we said that we would put kind of our times over here and our like f of whatever over here. I'm going to kind of just make a little list here, and I'm just going to list my times. And what I'm looking to calculate here is, well, what is the distance that the squirrel has traveled at these particular times? So if we go back to the t is equal to 0, well, here's my squirrel at t is equal to 0. It hasn't traveled any yet. It hasn't moved. We're still kind of at our starting position. So our distance at t is equal to 0 would just be 0. Our distance at t is equal to 9 is going to be this entire accumulation underneath the first part of this curve. And in this case, you can split this up into two triangles if you wanted to in a rectangle. This is actually a trapezoid, so we could use the trapezoid area formula. Remember that the area formula of a trapezoid is 1/2 base 1 plus base 2 times the height. So that's what I'm going to kind of use to calculate this distance here from t is equal to 0 to t is equal to 9. So it looks like my 1/2, I'm going to call my base 1 to be the 9 down on kind of the bottom base. My top base to be, looks like 5. And the height of this is going to be 20, because that's what my distance is from 0 up till the kind of top base of my trapezoid here. So my height is going to be 20. So it looks like it's going to give me 1/2 of 14 times 20. So 7 times 20. So that would give me my area to be 140. So at time t is equal to 0, the squirrel has moved 0 units. At time t is equal to 9, the squirrel has moved a total of 140 units. So then I want to calculate, well, what is the distance that the squirrel has moved at t is equal to 15? Well, we already know that this distance from t is equal to 0 to t is equal to 9, we've moved 140 units. Here's where this area below comes into play. So this area above is always going to be a positive area. But down here, if we were to calculate the area of this trapezoid, you'll notice that your height is now going to be a negative, because this distance from 0 to -10 is really going to give us a negative height of our trapezoid. So this area underneath the curve, the area that is kind of trapped between the curve and the x-axis when the curve is underneath the x-axis, is actually going to end up being a negative area. And the reason that that happens is because in that time period from t is equal to 9 to t is equal to 15, the squirrel is actually going to be moving left here, or it's going to be moving backwards, or it's going to be moving in a negative direction. So in this first area that we calculated, we were actually moving in a positive direction because the v of t function was above the x-axis, or v of t was positive. Down here, our squirrel is going to be moving in a negative direction because that's where our V of t is negative. So when we go to calculate what this area is, we're actually going to be using this negative 10 as our height. So if I calculate my 1/2, I'll call this base 1 to be, looks like 1, 2, 3, 4, 5, 6 units. Plus this base to be 1, 2, 3, 4 units. And then times our height of negative 10. It's going to be 1/2 of 10 times negative 10. It's going to be half of negative 100, which is going to be negative 50. So this area down here below the x-axis is going to have an area of negative 50. So if I want to know the squirrel's accumulated direction or the accumulated distance that it's traveled, we know it's moved 140 units to the right, but then it's moving negative 50 units, or it's going back 50 units to the left. So when I go to calculate the distance from t is equal to 0 to t is equal to 15, I'm going to add both of these together with the positive direction being positive and the negative direction being negative. So my t is equal to 15 accumulation is going to be the positive 140, but then I have to subtract out the 50 because that's when the squirrel is actually moving backwards, or it's moving in a negative direction. So at t is equal to 15, we've actually moved an accumulated distance of 90 units. We're still in the positive. We're still kind of to the right side of where we're starting, but the squirrel has moved forward, but then it's moved a little bit backwards. So then if we want to know what the distance is at t is equal to 18, well, we already know the distance from 0 to 9. We know the distance from 9 to 15. We just need to know what this distance or this area under the curve is going to be from 15 to 18. And here we can go ahead and split this up. I'll split this up into a triangle right here and the rectangle right here. So my triangle, 1/2 of the base of 1 times the height of, looks like my height is going to be 10 here. So it looks like the area of this little triangle here is going to be 5. And then my rectangle has a base of 2 and a height of 10. So it looks like this area is going to be 20. So from 15 to 18, it looks like my accumulated area is going to be 25. So if I want to know the entire total distance that we've traveled from 0 to 18, I'm really just looking to add all of these together. So positive 140, negative 50, and then positive 25. So positive 140, negative 50, plus 25. That's going to give me a 90 plus 25. So it looks like my total distance moved from 0 to 18 is going to be 115. So to actually answer part B, well, we want to know at what time in the interval is the squirrel farthest from building A. So what is our maximum distance here? What is the total distance or the farthest distance that he's moved? Well, it looks like that's happening at the t value of 9, because that's the largest distance that he's moved in that time period. So I'm going to say at t is equal to 9, the squirrel is farthest from the building. It's also asking us how far from the building is the squirrel this time. Well, we know that its distance is going to be 140. So at a distance of 140 units. And then part C is asking us to find the total distance the squirrel travels during the time interval 0 to 18. Well, guess what? We already calculated that because we know that that's just the accumulated or the total areas all added together. And we did that in the last part here. So the total distance in the interval is 115 units. So that just means that again, the squirrel has moved to the right 140 units, it's backtracked a little bit and moved to the left 50 units, but then it continues moving in a positive direction 25 units. All right, so I'm going to have you guys try some of these accumulation problems for homework, and we will talk about them tomorrow. Let me know if you have any questions.